let's see. Now, the big question should be, so what? Meaning, we've learned about mean absolute deviation. We've learned about standard deviation. What for? So what are these standard deviation, including mean absolute deviation? They really are different ways to measure the same thing. And what do they measure? How close or how far apart the data is. So typical data, how typical is it? Is this thing, are they mostly the same? Are they very different? It tells us how close to the mean an element is. So we can look at each data point and say, well, is this data point close to the mean? And we did that, I think, on the first day that we looked at it, right? We had kids' ages, and I can't remember what they were, the 10-year-old, the 11-year-old, right? Whatever we had, and we figured out, there was a 0-year-old, we figured out a mean, I can't remember what it was, let's pretend it was 12 or something like that. And then you could say, oh, well, this kid is 2 units under the mean. This one is 1 under the mean. Maybe there was like a 20-year-old. That kid is 8 units over the mean. And what are the units here? I guess we're talking in ages, so it's like years or something like that. Well, the idea is if we have the same units for all our data, it's very easy to compare it. But sometimes we don't have the same units, or it's on a different scale, or there's just something different. But we still want to compare the data. And that's where this thing that we're looking at next is. What we do is we say, how many standard deviations away from the mean is a data point? How many standard deviations, right? And that's what we're going to be looking at next. Now let's just review what standard deviations kind of tell us. So a small standard deviation in one state of data means that there's less variation when you compare it to another with a large. And I think we looked at basketball players, right? So if you look at the heights of basketball players, right, we did this. So if one of them has a standard deviation of 2, and the other team has a standard deviation of 8, what does that tell us about the different heights on these teams? Well, yeah, say it again.
The other one's really short and the other one's really tall.
Well, does it tell them who's short and who's tall?
No.
No. What does it tell us, Danny? Is that what that tells us?
No.
What does it tell us?
The average.
No, it's an average of what? What does it tell us, Claire?
It's showing that the two people in the basketball team are around the same height.
They are around the same height, and on this team, their heights are more different, right? Their heights are less alike than on the first team. That's what these numbers tell us. And if the MAD here was, I'm making up numbers, 1.6, and if the MAD here was 7, it tells the same thing. So they basically tell the same thing, we just arrive at their values in different ways. But it's how alike or how different is our data. That's what MAD and standard deviation tell us. So let's look at this example here. Not on your notes, we're just going to look at this for a moment. Okay, so we've got data set 1, the number of basketball players who showed up at a particular field. I think that's what's happening here. A number of basketball players who showed up on the field on a different day. What kind of inferences can we make? What are inferences? Do you know what that means? Like from English class, what does that mean? Yes, it's more like what does the data imply? So what is the data trying to tell us? So the first thing I noticed was the means are the same, right? So it says on average 45 players show up at each basketball court. That's what this is telling us. So that doesn't really give us much information, otherwise the average number of players shows up is the same. But which data set has the smaller variance in standard deviation? The left one, right? This one, the variance is 106.1. Remember, you take the square root of variance to get standard deviation, or if you have standard deviation, you square it to get that. That's smaller than this one. So what is that telling us? No, I gotta get you quiet. Well, what does that mean? It's got, let's just look at standard deviation, forget variance. this standard deviation is 10.3, and the mean absolute deviation is 9.1, right? They should be close. And this one is 20.5, 16. Those are the standard deviation and mean absolute deviation. So what is that telling us? She's like, I know she's got it. She's like, well, if this number's smaller, that means that the number of people that showed up each day was pretty close to 45 each day, or more close to 45 than on this side. Maybe one of these days we had 2 people show up, on another day we had 60, whereas on this one we're expecting them more to be just maybe a little above or below 45 showing up. Less variability on this one. Each day closer to being 45 than on this side where we can have a lot of variation. Okay? And when I look at the pictures, this is showing, these are the number of people that showed up each day. Are we clustering closer to that 45 mark? Look how it's close together. And then this data is farther apart. And that's what standard deviation, mean absolute deviation, trying to tell you. Okay, that's kind of the big idea of all this. Let's look at this one again. This one is not on your sheet. We're just going to look at this. So Maya represented the heights of boys in Mrs. Constantine's and Mrs. classes on the line plot. So this is a line plot. So one person was 64 inches tall, another was 65. We had 3 people who were 66 inches tall. I think we've seen these kinds of plots before. No, you never saw this before?
No, we haven't seen this.
No? Yes? Some people say yes. Some people say, do you have?
Yeah.
Okay. Well, here's what it is if you haven't. It's just saying 2 people were 67 inches tall. 1, 2, 3, 4, 5 or 68, right? It's called a line plot. So how many elements are above the mean? The mean is 68.4. So how many of these heights are more than 68.4? Ryan, what do you say? 5. 5, how'd you get that?
But it's just those from 68 to the middle.
So 68.4, right? So how many are above the mean? That's this way, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, right? How many are below the mean? Claire? 12. Right? So if this is our mean, I'll put a little mu here. That's below, that's above. How many elements fall within one standard deviation of the mean? What? Okay, now here's where we're going to start counting by standard deviations. See how our standard deviation, if you were to calculate all this out and run it through the calculator, the sigma comes out to 2.3. So what do they mean within one standard deviation? It means 2 to the right and 2 to the left. If you take 68.4 and add 2.3 to it, what do you get? And that's a 70.7. So over here, that's if you add 1 standard deviation, you get here. Now, is that 1 standard deviation from the mean? Because you could be this side of it as well. So you're going to take the 68.4 and subtract a standard deviation. So 66.1. So somewhere over here. That's if you subtract a standard deviation. First of all, before we answer any questions, do we see what I just did here? 1 standard deviation from the mean means you're 1 standard deviation above or 1 standard deviation below. I'm counting by 2 points. So how many points are within 1 standard deviation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's also 12. It's not the same 12 as this though, right? 1 standard deviation. Is that what you're going to say? Yeah. Questions? Does that make sense? This is kind of a key thing to what we're doing today. I'm counting by. Now what if I wanted to say how many 2 standard deviations away? What would I do then?
4 points.
What would I do then? I add another 2.3, right? So if this one is 70.4, add another sigma. In this case, that's 2.3. That gets me over here, and that would be 2 standard deviations. deviations, but that's just above. To be within 2 standard deviations, I could be below. So this 66.1, I'm going to subtract another standard deviation. Oh, that's a new 63 somewhere over here. 2 standard deviations now. Yes?
When you do the standard deviations, you have to find both ways or
Yeah, both ways. Because you think about being within 1 standard deviation, I could be above it or I could be below it. So you go both ways.
Will it ask for both or below?
No, if it says how many fall within 1 standard deviation, you're expected to know what that means, which is above or below. So that's what the definition, 1 standard deviation means above or below the mean. Anybody follow that? Thank you, 1 person. Okay, that's something.
Sure.
2? All right, let's keep going. And remember, you're supposed to be asking me if you're like, what? But that's your job. Right? Yes, sir.
For the last one, I really needed to know how the elements fall, fall within one standard deviation.
This part, how many elements fall within 1 standard deviation? What that means is if you have a mean, let's do a simple number. If your mean is 10 and your standard deviation is 2, so 1 standard deviation away from the mean would be at 12 and at 8. Now how did I get there? I added a standard deviation and I subtracted because now I'm within 1 this way and within 1 that way. That's what we're doing. Yeah, so with simpler numbers, maybe it's easier to see. Does that make sense for you? It's okay if it doesn't. You can look at it some more.
What about the final?
What about the, well, so I just made simpler numbers so you just see it up here.
What about, like, would you just subtract all 3 from it?
Up here, that's what I did. Yes,
Okay.
that's what I did when I
That
did
was
that.
much more complicated.
It's much more complicated than it. I'm counting by standard deviations. What about if I wanted to be 3 standard deviations from the mean? Well, what would that be? Well, 2, 4, 6, right? So I'd be up at 16, right? That's 3 standard deviations. And then 2, 4, 6 the other way, that would be a 4, right? And that would be 3 standard. So I'm counting by sigmas. Counting by sigmas. And this is called a z-score. A z-score also has another name. You might see it referred to as a standard score. But it tells you, this is the definition of z-score, and this is important. Z-scores say how many standard deviations above or below the mean of a particular data point is. Now we did this with just units. So this was when we calculated MAD. If our mean was 12, and we wanted to know this kid is 15 years old, how many from the mean? We said 3, right? 3 units above the mean. Well, we're not counting by these units. We're going to count by standard deviation. So here's a formula for it, and it's on the formula sheet I gave you, which means, you know, you'll have it with you on any test you take. And the way you find the z-score is, first of all, x minus mean. Does this look familiar at all? Where have we seen x minus mu before? What? The MAD, and the variance, and the standard deviation. This is called a deviation. And it's just distance, that's this. If this is 15 and the mean is 12, it's plus 3 away, right? If this is a 10, then that's minus 2, right? Right? It's just saying how far above or below. When I divide by standard deviation, now it's telling me how many standard deviations from the mean, not just how many units away. And if you're a positive z-score, that means you're above the mean. And if you're a negative z-score, you're below the mean. Maybe. Okay.
I get that.
You get that? Okay, so let's do an example here. Let me see if this is on here. Yeah, this is on here. So I am on page 5. Right, we're on page 5 on here. If you're following along, I hope you are. So, middle-ish there, middle top. A set of values. So I don't even know what they are. It means that I've got some x1s and x2. Right? I've got a whole bunch of data points. I don't know what they are, but I know its mean is 85, and I know its standard deviation is 6. Somebody's talking over there. Find the z-score of the value 76. Now, what does this even mean? Okay, so I tried to make a little picture of it the best I could. So here's my mean, right? 85 is the mean. Standard deviation is 6. So if you add a standard deviation, where is that point? Right here, 85 plus 6. And then what about minus a standard deviation? 79, right? Because I'm 85 minus 6. That's one standard deviation. Now 2 standard deviations, you add another 6, right? So that would be 97. Or I subtract 6, that would be 73. So just that. Does that make sense? Are we following that much? Now think about the value 76. It's here, right? So how many standard deviations from the mean is that? Well, that would be minus 1 standard deviation, and that would be minus 2. It's somewhere between minus 1 and minus 2. It's a fractional distance away. This formula will tell me exactly what it is. The z-score is x. What do I mean by x? X is always what in statistics? What's x always? The data point, right? So what's our data point? 76. That's my x. Minus my mean. What's my mean? 85. And then divide by standard deviation. So what's 76 minus 85?
Equals.
It's a negative number, right? And that makes sense. Don't I expect it to be negative? 9 over 6. And I put that in my calculator. This is one of those cases you do want to turn it into a decimal. Negative 1.5. So this says 76 is 1.5 standard deviations below the mean. That's what negative is. Now look at the picture, is it? Yeah, that looks about right. So it's just telling, if you were to count by standard deviations, 76 is 1.5 standard deviations less than the mean, below the mean. Well, 79 is 1 standard deviation below the mean. So 76 is further away from the mean. And this tells me exactly, negative 1.5. Right, can we see what's between negative 1 and negative 2 standard deviations? Okay?
Yeah.
Yeah, follow that?
Yeah.
Good. Let's try another question here. This is still on page 5. The following numbers are metabolic rates. Ooh, that sounds good. Of 7 members who took part in a study of dieting. Oh. So units are calories for 24 hours. So this is how many calories they had per day. Okay, so how many standard deviations above or below the mean is 1460 calories? All right, wait a second. So one person had this many calories, another had that. And data points. So what you need to do now is find these values. First find the mean standard deviation. You're going to use your calculator, right? So go ahead, plug these numbers into your L1, do your StatCalc 1-bar stats, and come up with these values. Okay, working it? Everybody's doing it? Not just me.
I'm working it.
Good. Work it, work it.
Working it and working it for all these numbers.
Easier if you look on, oops.
We're already there.
So, right. Well, look on your paper, right? Your paper has all these numbers on it. On your paper on page 5, because I can't move this thing. It's in front of me.
Oh, it does say it.
What's the matter?
You're smart. The answer's on the paper.
Well, keep doing it. You need to do it to make sure you know how. This is not about getting the answer. It's about knowing how.
Can you get the answer on here?
Stop putting them up there. Just hang on.
Don't worry, I already got that.
Everybody checking their values? Check your values. I know I've typed them in wrong a few times. Okay, got it. I'll put it right. Let's see. I'm doing my 1-bar stats. Okay. 1600 plus approximately 175.2. Is that what we got?
Yeah.
All right, so z-score says x minus mean over standard deviation. What's the x?
1600.
That's mean. 7. How many standard deviations above or below the mean is 1460 calories? So what's the data point that I want a z-score of? What's x? I'm using this formula. I have a mean, right? I have standard deviation. What's x? What do I want a z-score of? There's only one in this question. Here's your question. Read it again. What does it say? How many standard deviations are above or below the mean? Above or below the mean is 1460 calories. So what do I want a z-score up? What value? That's your x. So x minus mean over standard deviation, 1460 minus 1600 over 175.2. So where did all these other numbers come from? Where did x minus mean, we calculated it, standard deviation. This should approximately be what, negative 0.8-ish, right? Approximately?
How do you get 1460?
Because it says, tell me. So find the z-score of this data value. So what's happening here? So here's my mean of 1600. If you add 175.2, what's that value? I don't know. Whatever that is. 1600 plus 175.2. So it's over here someplace. About 1775-ish, right? And then over here. All right, let's find below now. What's 1600 minus 175.2? I don't know, that's somewhere around 14 something or other. What is this these days? 1600. And I'm just subtracting the standard deviation because we're counting by standard deviation. 1425, let's call it, just for fun. Somewhere in here. That would be one standard deviation. My number is 1460, right? So do we have some idea? We know it's going to be a negative number. It's below the mean. And here is minus 1. So it's a little bit bigger than minus 1 standard deviation. So does this look about right? Minus 0.8? Yeah, I think it does. The 1460 is over here. So that's where it's telling you how many standard deviations away from the mean. Now, how many points are within 2 standard deviations of the mean? Well, let's see. Figuring out what 1 standard deviation is, how would I find what the limits are for 2 standard deviations? 2 times. Yeah, she's saying, why don't you just take 1600 plus 2 times your sigma value, right? So what do you get? 1600, add 2 times your sigma value of 175.2, 1950.4, that's somewhere over here. So that's 2 standard deviations. And you go the other way? You can subtract it too. Because we want to know below the mean as well. 1600. Or within. So it says something else. It says within. Wow, this is not a nice program. 175. Okay. I am not enjoying this calculator, so I'm going to get rid of it. This is the expensive calculator. Where's my little free one of these? So 1600 minus 2 times. So what am I doing here? I'm saying your mean minus 2 sigma. That's what I'm doing. 1249.6. It's over here someplace. And that would be 2 standard deviations. So it wants to know how many points fit within that range. How many points are between 1249 point whatever that was and 1950? Well, is this between 1240 and 1950? Yes. Is this between that 1249 and 1950? Yes. Yeah, I can't read it either. What did it say? Well, let's say 1250. For fun. That's minus 2 sigma. And 1950, just so we can see it, that's plus 2 sigma. So I'm looking for how many points are between 1250 and 1950. Yes? Between 1250 and 1950? Well, all of them are. 1, 2, 3, 4, 5, 6, 7 points are within 2 standard deviations. Now, what if we wanted to know how many are within 1.5? I need to find those boundaries, right? So how would I find those boundaries? So how would I find the boundaries? Yeah, fine.
You could use the double sigma.
Here's what I'm doing. I am saying now I want to be at the mean, but I want to be 1.5 standard deviations above. So 1.5 times your standard deviation value, add that to 1600, 1862.8. So that's 1.5 above. And then I want to see minus 1.5 below. So I'm going to do 1600 minus 1.5 standard deviations. And so that's like 1337.2, is that what you got? This is 1.5. So now I look at my points. It is 1792 between 1337 and 1862. Is 1666. 1362. 1614. 14. Are they all going to branch again? No. This one is above that. If this one works, so only 6 points are within 1.5 standard deviations from the mean. So you're basically counting standard deviations, and they could be fractional. If you have a calculator, that's okay. Question? Where am I? I mean, I know this is messy looking. Let me erase some of this. But you're just counting by standard deviations. Add and subtract, yes. So starting at your mean, you're going to add, if you want to know how many within 1 standard deviation, so add and subtract 1 standard deviation. Those are your boundaries, and see which data points fit in between. If they want to know who's within twice, then you do 2 standard deviations above and below. Count how many fall within those boundaries.
So add and subtract it, so 175.
Well, because that's my standard deviation.
And then I take the third numbers up there.
Right.
I
Right. You just see if they fit within our boundaries. This is how you're 1.5 below. This is as big as you can get for 1.5 above. So if they fit in between, they are within 1.5 standard deviations of the mean. I think I have another one. Oh, this is a great question. This is, I think, a good example of when z-scores become important-ish. I know it's a silly example, but it's still good. So John weighs 220 pounds, and his dog Fido weighs 90 pounds. So if human males weigh on average 160 pounds, that's the average, with a standard deviation of 20 pounds, and all dogs of Fido's breed have an average weight of 80 pounds with a standard deviation of 5 pounds, how do John and Fido compare relative to their populations with respect to weight? So, I mean, like a small dog, like if a person gains a pound, you probably wouldn't see it, right? If you have like a Chihuahua and it gains a pound, they come out, right? I mean, it's a little creature, a pound is a big deal. Big creature, not so much. So using the same scale of reference isn't good when you're comparing species. So if you look at John, so the average is 160 and he is 220. He's overweight. Fido, the average is 80, but this dog is how much? 90. So he's overweight too, but who's worse? And you can't just take the difference because 10 pounds in a dog may be like 50 pounds in a human. We don't know. Right? Because it all is relative to the size of the species and all those things. So we do z-score. So we say how far above the mean, how far above the mean. So let's see, this would be the x, because that's our data value. What's the standard deviation for man? 20 pounds? And then for this dog, the standard deviation is 5. So let's find the z-score. X minus mean over standard deviation. 220, 160 over 20. Yeah, it looks like 2. I think that's 2 standard deviation. So these 2 standard deviation. Oh, I did that. That's 3. Sorry. 60 over 20. And now this dog is 90 minus 80 over 5. Who's fatter? Who's in worse shape? John. He's 3 standard deviations above the average weight of a person, whereas the dog is 2 standard deviations above. We now can compare things that normally are very difficult to compare. Okay. All right, so there's like a use of this. So we're getting a little bit late here. I'm just going to leave this for here. We'll finish this next time. Never mind. We're going to do this example. Given a set of data with a standard deviation of 3 and a mean of 9, what would the value of an element be? So just watch this. We know this formula. Your data value minus the mean over standard deviation gives you your z-score. Well, what are they giving you? They're giving you the standard deviation of 3. The mean is 9. And what's this? The z-score is 2.5. So plugging in the numbers, standard deviation is 3. I gotta solve for x. How do I do that? Multiply both sides by 3, right? Notch that out. This is where your math calculation skills for equations work. So what do we get here? 7.5 equals x minus 9. Add 9, add 9. 16.5 is x. Oh, who has a z-score of 2.5? The value is 16.5. So being able to